Okay, converting concentrations. A lot of different ways of doing this. I'm going to give you several different problems. There's more in the book. If you're in my lecture, you'll see more in the on-ground, but of course, everything, all the different variations are found in the book. This will be a good bunch of them, though. All right, so when an experiment calls for 125 grams of HBrO2, so bromous acid, that is 15% bromous acid by mass. How many grams of bromous acid is this? So how many grams of, and then how many grams of water? So the expression is the mass percentage of solute equals the mass of solute divided by the mass of the solution, which is made up of the solvent and the solute. So mass of the solution times 100%. Well, they said that they, so let's put that in. The mass of the bromous acid divided by the mass of the solution, which they told us is 125 grams, times 100% should be equal to 15% of the bromous acid. So dividing through by 100% and rearranging, we end up with the mass of the bromous acid is 0.15 times 125 grams, which is 18.8 grams HBrO2. The mass of the water is then going to be 125 grams, because that's the only other thing that's in the solution, so the solution is 125 grams minus 18.8 grams gives us 106 grams. And you could have also found it by doing 0.85, since it's 15%, and if there's 15% of the acid, then it's 85% of the water, times 125 grams. And it has to come out to be the same thing, but rounding might have slightly changed it, so I just want to do this out. Yeah, so this would come up to be 106.25, which would be 106 grams. So you can do it either way. The first one you'll have to find by this equation, but the second one can be found. As long as there's only two things present in the solution, you can find it by difference. Okay, so a lot of these guys to do. Find the molality of a solution that is 15 grams of ammonia and 185 grams of water. So molality, not molarity, but molality equals moles of solute divided by kilograms of solvent. And the reason we use molality, moles of solute doesn't change with temperature, neither does the mass of the solvent. Molarity, though, has liters of solution, and liters of solution will change with temperature. The volume of liquid changes with the temperature. So molality is temperature independent, and that may be important if you're doing research that takes you inside and outside of your lab. So inside your lab it might be 22 degrees Celsius, outside your lab might be 5 degrees Celsius. So you want to have a concentration you can count on to be the same no matter what the temperature is. So what we do, we need to know we know that our solute is ammonia, NH3, and there's 15 grams of it, so we need to change to moles of that solute if we're going to find molality. So this is 17, and I've done these calculations out previously just to speed things along, so I'm doing them out so that you can see it. It's always nice to see someone working through the problem. But if you're wondering why somehow I know how to do this so quickly, it's because I've done them before. So 108, so that gives us moles of NH3. Then we need kilograms of solvent. Well, they told us that we have 185 grams of water, and I'm sure you can do this one without using this conversion factor, but you just shift the decimal place, but I'm going to do everything out. And then the molality, lowercase m, should mention that rather than the capital M, we use the lowercase m. And this is 0.882 moles of ammonia divided by kilograms of the solvent rather than liters of solution. So we end up with 4.77 molal NH3. Okay, the next calculation involves mole fractions. That's another type of concentration, or another way of keeping track of the concentration. Calculate the mole fractions of HCl in water. You have 2 grams of HCl and 20 grams of water. Well, if we're going to use mole fractions, we need to have the moles of each of the species, the solute and solvent. So this is 36.5 grams of HCl is 1 mole of HCl, gives us 0.0548 moles of HCl. And then water, so I haven't explained what mole fraction is yet. I will, so don't worry about that. But first, if we're going to have mole fractions, it sounds like we need fractions of moles. So we need to be in terms of moles, and that's what we have here. Okay, now the mole fraction, and I'm not sure if your book uses this term or not, but capital X represents mole fraction of HCl. So we have capital X for mole fraction, and the subscript is to indicate which species. We have moles of HCl divided by total moles. So moles of HCl and water. So we have 0.0548 moles divided by 0.0548 plus 1.11 moles. And this comes out to be 0.0470. That's a fraction. There's no units of measure. We've canceled them. So it's just a fraction. We can convert that to a percentage. It would be 4.7%. But mole fraction is, and that would be in moles rather than grams. So it would be a mole percent. But we leave it as mole fraction. Now, the total number of mole, just like in percentages, the total percentage has to be 100%. The total number of mole, the sum of mole fractions has to equal 1. So to find the mole fraction of water, we could just take 1 minus this number. But let's do it out. And that would be actually the smart way to do it on the exam because it saves you time, but I just want to do everything completely out. So you'll get the full feel of it, but you can certainly save yourself some time doing it the other way. But this comes out to be 0.9530. And if you add these up, they equal 1, and they have to. So if there's only 2 species and you add these up, it has to equal 1. If there's 2 solutes, let's say we also had HBr in here, then it would have a mole fraction, and all of them would add up to 1. So no matter how many species you have in the solution, they have to add up to 1. Okay, so that is the mole fraction. Now we want to convert from one to another. So we want to convert 0.150 molal NaCl to mole fractions. So that 0.150 molal NaCl equals 0.150 moles of NaCl over 1 kilogram of water. We're going to, though we don't say it, oh yeah, it does say there, water. But we always assume aqueous solution unless otherwise stated. So just assume, you can always assume that on the exam, that if it's a solution, it's water. If I want to use pentane or some other solution, other solvent, I have to say it. So then we have, now this is, so this molal indicates that we have 0.15 moles of sodium chloride, so we already have the moles of sodium chloride. We know that if we have mole fractions, we have to determine the number of moles of each species. Well, we have 1 kilogram, so the moles of NaCl is already set up for us. If we use 1 kilogram of water, we're free to use whatever volume we want, but might as well use the one that's part of the definition. 1 kilogram of water is 1,000 grams of water. And then if you get rid of that because it's no longer equal, if we just change to moles, we have 55.6 moles of water. So the mole fraction of sodium chloride is 0.15 moles over 55.6 plus 0.15 moles. So you can see it's going to be pretty small because the amount of water is 55 moles of water. So the mole fraction for sodium chloride is teeny tiny, and then so the mole fraction of water should be pretty large. It's going to be 55.6 over 55.6 plus a tiny little bit, so it won't be 1, shouldn't be, but it'll be pretty close. It'll be 0.997, and I just went out on the calculator so that we match up exactly with what we have here. So these add up to 1. They don't necessarily have to. With some rounding that happens, this might have ended up as a 268, and if this ended up as 730, not 0.99730, we'd be off. But if it comes up, instead of getting 1, you end up with 0.993 or something like that. They're very, very close to 1. Assume that you're correct. You can always go back and double check your work. But rounding can have an effect. Okay, so we have, now we're going to take a solution that has mole fractions and convert it to molality. So we're going back the other way. So the mole fraction, so we can write them, KBr has a mole fraction of 0.14. And that's no units of measure, just a number, because it's a fraction. A mole fraction then is moles over moles, so moles cancel, so the fraction will always just be a number, and it should be between 0 and 1. Now, if we, for 1 mole of solute and solvent together, or I should say a total of 1 mole, that means that 0.140 times 1 mole, so I'm just saying we have a mole of we take that solution and we get a mole of KBr and water together, total. Then that means in that 1 mole of KBr and water together, we should have 0.140 moles of KBr and 0.86. So we went from a fraction, and we just took, we can take any amount of moles we want. We can have made this 86,000 if we wanted, or 0.0035. It'll all come out the same way, because we're taking it from a solution that's mixed together. So, but I thought, well, why don't we just take 1 mole of this, make it easy on ourselves. So the mole fractions then take on units of measure. So that's where, and students have a little trouble with that sometimes, because it seems like there's something missing. Well, it is. You have the mole fraction, but that works for any amount of the solution. And I'm saying since we can take any amount we want, let's just take 1 mole and make our lives easier. So now we already have we know the molality is moles of KBr over kilograms of water. Well, by changing over to moles here, using 1 mole and the mole fractions, we have this part is done. That's here. Then we just have to convert moles of water to kilograms. So 1 mole of H2O is 18 grams, and this comes up to be 15.5 grams, which is equal to 0.0155 kilograms. So now we have kilograms of the solvent. So 0.14 divided by 0.0155 kilograms equals 9.03 molal for the, what is this, KBr. I'm so used to using NaCl. No, okay, in case I did that, it should be KBr, but I used it throughout, so good. And then the last one, you can see that we're already at 14 minutes here, so that's why I've chosen to do all this stuff out previously. So if I made any mistakes on the calculations, just keep in mind the setup is correct. Now, let's do the tougher ones here. The solution is 0.580 molal oxalic acid. What is the molarity of the solution? So we're going to go from moles of the H2C2O4 over kilogram of water to moles of H2C2O4 over liters of solution. Alright, so the big thing here is that the moles are already set, so this 0.58 will go directly over. Now we got to convert kilograms of water to liters of solution. Well, kilograms to liters, that's mass to volume, so the density should be involved, and that's why we have it here. So what we do, we need to know the mass of the solution. We only don't know the mass of the water, but we add in the mass of the H2C2O4. That gives us the mass of the solution. The density will allow us to convert to liters. So that's what we do. We have 0.580 moles of H2O, C2O4. So we're trying to determine the mass of the solute. We already know the mass of the solvent. That's given in the definition, 1 kilogram. We'll add that to it, to the kilogram, and that gives us the mass of the, that gives us 1 kilogram is 1,000 grams. So this is due to the water, this is due to the H2C2O4, the oxalic acid, and that's 1,052.2 grams of solution. Now we know the mass of the solution. We know the density of the solution. So together, and I didn't get rid of any significant figures yet, just kind of carrying them through. And this will be 1,030 milliliters, which is 1.03 liters of solution. So it's a little trick that we have to do. Figure out the mass of the solution from the molals. We know we have 1 kilogram of the solvent. Convert moles of solute to grams. Add those up. That's the mass of the solution. Take the density of the solution to create the liters. And then we finish up. We knew that we had this many moles of H2C2O4. Divide by this. And we get 0.563 molar H2C2O4. Okay. Now going from molals, going from, I should say, molarity to molals is pretty much the opposite process. You know, it's the reverse of what we did previously. 0.265 molars is 0.265 moles. I'm going to just make this T acid, tartaric acid, over 1 liter of solution. Well, we know that we have, so 1 liter of solution equals 1,000 mils, and 1,000 mils of solution times the density of the solution, which is given above here, gives us mass. So now we're in terms of mass of solution, not mass of solvent like we'll need for molals. We'll need kilograms of solvent. So this is the tartaric acid and the water together. So now we have to subtract off the mass of the tartaric acid. That will give us just the mass of the water, which we convert to kilograms. And we already know what the moles of the acid is. That's right there. So that'll go on top of our molals, or to solve for molals. So I'll call this T acid. It's 150 grams, or that's what I calculated it to be. So this comes up to be 39.8 grams. And I got to move really fast because we're running out of time, but if I've made a mistake in the calculations, there's a lot going on here. Just let me know. I'll tell you. I double-checked everything, so I believe everything's fine, but normally I like to just go through some of the calculations as even though I've done them previously, just to double-check. But this is the mass of the solution. We found that with the volume of the solution times the density gives us the grams of solution. Then we subtracted off the mass of the solute, so we just had the mass of the water. And then we're done. We know how many moles of the T acid we had, the tartaric acid. And then we know the mass of the solvent. And we've now converted molarity to molality.